So this is it. This is our very last video, very last lesson for the extra topics chapter for AP Calculus. And we're going to dive into looking at imaginary numbers. And this is a huge field that you're going to spend perhaps an entire course, maybe two, in science at university doing. And we are going to just scratch the surface, the tip of the iceberg. But you get a chance to see what this is all about. So what do we know about imaginary numbers from just math here at Penn High? Well, people have been saying these are all about the square roots of negatives. So let's put that in here. And then I'm going to grab my calculator and just see what it thinks about it. You know, what is the deal with square roots of negatives? So I take my calculator and fire it up. Let's try it. Let's do the square root of, I don't know, negative 49. And when I do that, it gets very upset with me. It's like, look, this is not a real number. Real numbers, we were told, you know, early on in math here at Penn High, real numbers are numbers that you can find on the number line. And I kind of understand how number lines work from elementary school. You know, as in elementary school, we first started looking at number lines. We didn't have any negatives at the beginning. And you get all the little kids lined up, and you're like, ooh, look at all the numbers. And oh, I love the little logo down there. School is a happy place. Yeah, right up until you get into high school and your math teacher starts giving you like set notation like this, like show me all the x's chosen from these real numbers on the number line, such that x is sandwiched in between 7 and 12, including 7 and including 12. And the kids are all really stressed, right? And it's like, oh, it's not a big deal. You just need to go and pick like all these numbers, right? Okay, great. Yeah, we can do that. So that's the number line. I get it. And then in middle school, it's like, oh, hey, there could be negative numbers too. But yeah, this number line, a lot of teachers have it, you know, on their wall, and I can see all the numbers going from left to right, negatives to positives. Those are the real numbers. Any real number fits in there somewhere, sometimes in between those nice integers. These things are not going to fit on that number line. Well, they're out there, but they're not going to go on the number line. And if you're wondering, well, if they're out there and they're not on the number line, where do they go? Strangely enough, I'm not lying to you to say that they're actually kind of like up above the number line, or maybe even down below the number line. That's where these complex numbers, these imaginary numbers, are going to go and hang out. And let's go and take a quick little peek of how this deal actually works. Well, just like the number 1 is a very important number for real numbers, right? The unity number. We've got something like that, the unit number for imaginary numbers, and it's the number I. And people have just agreed that the number I, sometimes called J if you're an engineer, is equal to the square root of negative 1. Not negative 7, not negative 36, but negative 1. And if it truly is the square root of negative 1, then this should happen. If I take I and square it, I should end up, believe it or not, back at negative 1, because apparently it's the square root of negative 1. Now, if I just go to my calculator and say, well, do you know about this I thing? Like, what's the square root of negative 1? At first glance, my calculator says, no, I don't know what's going on there. That's not on the number line. Of course not. It's up above the number line. So you have to go and take your calculator and put it into university mode. And it has a couple of different modes for handling these kinds of numbers. So I'm going to hit mode, and down near the bottom where it says real, I don't want to just limit myself to only real numbers. I'm going to slide over and try this a plus bi thing and see how that works. And so I'm going to say, oh, okay, calculator, do you know what the square root of negative 1 is? And now it doesn't get all upset. It goes, well, you and I, we all know that that's I. And you're like, are you sure? Let's try it out. The number I is actually on your calculator. Okay, it's actually there. It's just down up above the decimal point. I can barely see it on this screen when it's that small, but it's up above the decimal point. It's a second function. And then I can say, hey, what if I square that? What do I end up with? And my calculator goes, well, of course, that's negative 1. So this is kind of cool. If I take this thing, which we just agree to call I, if I square it, I do indeed get negative 1. That checks out. Well, you can even do more interesting ones. You can say, well, what about like I cubed? What's that going to be? Well, you could think of that as being like an I squared multiplied by an I. And the I squared is just a negative 1, and then multiplied by the I. So that's actually just going to be negative I, which it turns out hangs out down underneath the number line from middle school. And so if I say, hey, calculator, did you know that? Like, what if I take I and cube u? It's like, well, that's negative I. Okay, great. Let's keep going. What if you were to do I to the fourth? Well, that's kind of like an I squared multiplied by an I squared. Okay, that's a negative 1 multiplied by a negative 1. Got some negatives that have now come around twice, and by the time we do that, now we're back staring at 1 again. Geez, trigonometry did that when we did derivatives with sine and cos. That's not actually an accident that they're the same. If I take this to the fourth power, yeah, I'm back to a 1. And by the same reasoning, if I was to do I to the fifth power, that's like I to the fourth power multiplied by an I. So that would just be a 1 times an I. That's just going to be an I. And my calculator knows that too. I say, hey, let's do I to the fifth power. And it's like, yep, just a plain old I. Okay, next issue. We're going to have to sort out a little vocab difference here between what we call imaginary numbers and complex numbers. Imaginary are numbers that they don't have any real part to them at all. And people would say, hey, these are going to be numbers of the form, like they feel like this. Numbers of the form, some number, let's just call it B, but then multiplied by an I. So if it has that feeling, then it's going to be an imaginary number. Now this B, this is just going to be a plain old number, if I can call it a plain number. It's just going to be a real number, a number that you'd find on the number line, but then that's bumped onto an I. Here are some examples. Here are some examples of numbers that are purely imaginary. Maybe 7I, right? Where I have that 7, that real number 7 out there in front of the I. They can be negative, like negative 2I. You could have decimals. You could say 3.4I. You could even do things like root 5 times I. Okay, those are imaginary numbers, sometimes called purely imaginary numbers. And then complex numbers are very flexible numbers. These are going to be, generally speaking, a mix of real and imaginary numbers. We'll certainly allow them to be that. Now I mentioned that your graphing calculator has a couple of different ways of working with these, of tolerating them and communicating to you about them. If I go back to mode, it had that A plus BI, that's the mode I'm in right now. So that's saying, hey, let's talk about these complex numbers in that format of A plus BI. So yeah, they're going to be of the form a real number plus a real number multiplied by an imaginary I. But the A and the B, they don't have to be integers, but they have to be decent real numbers. So here, an example or two of some complex numbers. It could be maybe negative 5 for the A plus 2I. That's a complex number. Or here's another one. How about 4 plus 3I? Yeah, another perfectly fine complex number. Now, when you are playing with these complex numbers, sometimes you want to talk about just the real chunk of it, or just the imaginary chunk, or maybe I should, to be correct, say the size of the imaginary chunk. And we've got a couple of operators that'll actually extract that information out. One of them is this one, this real operator. And into this machine, kind of like into sine and into cosine, you can put some values and see what you get out. Into this machine, I can put a nice complex number like negative 5 plus 2I, and it'll say, oh, thank you for giving me that complex number. That's pretty cool. Oh, you just want to know how big the real chunk of it is. Well, the real chunk is just negative 5. That's the real part of it. And your calculator will do this. I'm just going to clear this off. If I go let's make this a little bit bigger here. If I go into math, I can then slide over a couple of spots to complex. And it's like, all right, let's do some complex math on some numbers. And number 2 is going to be the real part. So it says, okay, the real part of who? And then I can put in there, yeah, I have -5 plus 2i. And it'll be like, oh yeah, that complex number? You want to know the real part? It's -5. Likewise, we've got another operator in the world of complex numbers. This one. It's going to go and find out the imaginary part, or maybe I should say how big the imaginary part is. So if I put in here -5 plus 2i, it doesn't actually say 2i, right? You might think, really? Like, that's the imaginary part, right? Well, it's only supposed to tell you how big the imaginary part is. So if I do this again and I go mode, or sorry, not mode, correction here, math, I'm going to slide over to complex. And now I'm going to pick the imaginary chunk and say, yeah, can you do that for -5 plus 2i? It'll look at the 2i part, but it doesn't tell me about the I. It just says, oh, the imaginary part of that, it is too big in terms of size. So it doesn't put the I in there, it just tells you the coefficient in front of that. Okay, so these responses back from both the real and the imaginary operator, they just tell you in a real number sense how big these things are. Now, here's where it gets really cool. Well, it's all cool, but now it's going to start to get cool, because a second ago I said that you can find these numbers up above and down below the classic middle school number line. These are where complex numbers reside. And now I want to show you how you can go and find those. So this is what we call the complex plane. This is really just like an XY piece of graph paper from Math 8 when you were just looking at, you know, like a Cartesian plane, graphing of a line. It's like that, except we've got 2 different axes going on here, not the X and the Y, but we're going to talk about, hey, how big is the real part to your number, and how big is the imaginary part? Your classic number line never had any imaginary part to it. When you were in middle school and in elementary school, we never worried about there being square roots of negatives in our work, so you were constrained. It's so sad, actually. You were constrained to only live along here. Well, we don't want to do that. We want to be open-minded. So, no, we want to go all over the place. So if somebody's got this number 4 plus 3i, you will not find it here on that elementary school number line. It's actually going to be up above it, because it's going to go here. We're going to go 4 over for the real part, okay, over to here. It's just like grade 8 graphing on a XY plane, and then 3 up for the imaginary part for the size of that. And that is what that imaginary, sorry, I should say complex number looks like. And it's not a bad thing to think of this number as being like a little vector, like it's that big and it's pointing that way. It's got a very particular angle to it. And we've all done Pythagoras in middle school hundreds of times, and we know that if you have a 3-4 triangle, it actually has a 5 for its hypotenuse. So 4 along the bottom leg, 3 up and down. Yeah, that does give you a little arrow length here of 5. That's how far that particular complex number is away from the origin, kind of away from 0, if you wish. The next number to graph looks like we've got a -5 plus 2i. Okay, yeah, that number, -5 for its real part, but a +2 there for that imaginary part, for the 2i. And it's not a bad thing to think of this as being like a vector, a little arrow that has a length to it. The length is a bit awkward. You'd have to do Pythagoras with the 5 and the 2, right? So 25 and 4. It's like root 29 or something for how long it is. And it's got a very unique angle to it as well. -3 minus 3i. All right. That complex number, 3 back and 3 down. That's going to go here. And yeah, I can think of it as being like a vector that looks like that. The size of that complex number, which we're going to talk about in a second in part 6, you'd do Pythagoras, and you'd say it's a little right angle triangle, 3 over, 3 down, so 3 squared is 9. Another 3 squared is 9, add them up, 18. This is like root 18, and it's got a very specific angle to it. Yes, you can polish up that root 18 and say, oh, that's 3 root 2. Yeah, whatever. The last one, 2 minus 5i. Okay, 2 over, and then 5 down. That complex number would be here. And yeah, it's a good plan to kind of think of that as being like a little vector, a little arrow. And it's going 2 over, 5 down. So if I do the Pythagoras on that one, kind of like the other one that was negative 5, 2i, we're going to also see that if you do the Pythagoras here, you're going to end up with root 29 for how big that thing is. Different angle, though, than that green one. And what you can see here, again, none of these fit onto that elementary school or middle school number line. None of them fit here, right? They're not going to go in this spot. They don't belong there. They're in more exotic locations, you know, up above and down below that middle school number line. Okay, well, I've mentioned that you can think of these as being like little vectors. And one of the things that you do often when you're playing with these complex numbers that have imaginary bits to them is you do look for their absolute value. And I want you to, for now, remember, this is just a half hour or so introduction to this. I want you to, for now, just think of absolute value as being the distance from 0. That's what it's asking. And when I say 0, I guess what I mean is like from 0, 0, from the origin. And so if you were to look at the size of this particular complex number that we had up there in blue on this grid, the 4 plus 3i, if you were to find its absolute value, sometimes denoted with a extra thick little absolute value bars, you'd be like, yeah, you know, not a big deal. It's just some middle school Pythagoras. We're going to go 4 squared. We're not going to put the I in there. We're just going to say, well, it was 3 up, right, along the I direction. And so, yeah, this is that classic 16 and 9 makes a 25. So this works out really well. This is just a nice, beautiful 5. So the size of that complex number is just a nice, clean 5. Okay, next thing. You are going to need to add and possibly subtract complex numbers. Very, very easy to do. All you have to do is just collect the like terms. Do it by adding if it's an adding question. Do it by subtracting if it's a subtracting question. So when it's time to do this, I would look at the 4 and the 2 for this first one and say, okay, both of those items there are the real parts. They go left and right in that complex plane. I'm going to go and just simply add them up. I wouldn't even normally write this step in, but I'd be like, yep, I got to go 4, and oh, it's an addition question, so I'll add on 2. And then I go and say, okay, let's collect up the imaginary part. What about the I chunk to this deal? Well, this one goes 3 up, and this one goes 5 down, and I literally collect the like terms. 3i added with, it is an addition question, added with negative 5i. I'm going to put those together. So 3i add with negative 5i, and yep, just going to then add those two things together, and when I'm done, I end up with 6, and it looks like minus 2i. And my graphing calculator would be perfectly happy to do that. If I was to say, hey, if you had 4 plus 3i, and you then wanted to add 2 minus 5i, it knows what it's doing. It's like, yep, I got it figured out. 6 for the real part, negative 2 for the imaginary part. Really the same plan if you're subtracting. It's just that you now have to subtract the deals when you put them together. So I would be looking at this going, all right, I've got to go negative 5 and then subtract a negative 3. Oh, and there's also this imaginary chunk where I'm going to go 2i and then subtract a negative 3i. It's the same logic, right? And then we'll just blend those two answers together. So negative 5 minus a negative 3. Negative 5 plus 2, we're still in the negatives by 2. And then looks like we've got a 2i plus a 3i. Well, looks like we've got 5i. And your calculator would be perfectly fine helping you out with that. So the game of adding and subtracting complex numbers, not really that interesting, just collecting up like terms. When it comes to multiplying and dividing, which we're going to do next, it's way more interesting. Read as a little bit more complicated. So let's go over the page here, and we'll take a look at multiplying complex numbers. You know, what's involved there. And I've got a couple of them here, and we'll see what happens when we multiply them together. You can check these on your calculator. Your calculator knows how to multiply these. It's totally fine. If in one word I had to talk about how do you do this, it would be that little saying we say from the math department, hey, you got a FOIL. We've got to double distribute. This 4 is going to multiply onto that 2. Oh, but the 4 is also going to multiply onto the negative 5i. And the 3i is going to multiply onto the 2, and the 3i is going to multiply onto the negative 5i. And you just do all 4 of those, and we'll polish it up when we're done. So this is going to end up being 4 times 2. Hey, that's an 8. And then my outsides, 4 times a negative 5i. So that's minus 20i. And now the middle term, 3i times 2. So plus 6i. And then the interesting part here, 3 times a negative 5 is going to be minus 15, but I'll just colorize this here a little bit. I times I squared. Uh-oh, I squared is negative 1. That's like we agreed that that's how it works. It's the square root of negative 1. So this is going to be 8 minus 20i plus 6i, so some imaginary chunks in the middle there. But this thing out here, it's not imaginary at all. The orange part, when I square the I get a negative 1, multiply that by the negative 15, and I get a positive 15. And then I put it all together and say, okay, how much real stuff have I got? Looks like I have 23. And then what about the imaginary? Looks like minus 14i. And my calculator could do that, right? If I was to say, hey, would you mind doing 4 plus 3i, and then can you multiply that by 2 minus 5i? It's like, yeah, I got that. 23 minus 14i. Okay, let's try that out one more time. Still multiplying. No dividing yet. So I'm just going to FOIL. So I'm going to have negative 5 times negative 3. That'll be a 15. And then my outsides. Negative 5 times negative 3i. 2 negatives. That's going to make a positive 15i, an imaginary component. Then the insides. Minus a 6i. And then the last. And you get kind of used to just doing this without, putting an extra step in there. This is going to be 2 times negative 3. That's a negative 6. But then there's an I squared. So as much as I'm tempted to write negative 6 from all my math experience, I'm actually going to write plus 6. Because it's negative 6 times the I squared. Negative 6 times a negative 1. And yeah, finishing it off. Looks like 21 plus 9i. All right, so that is multiplying complex numbers, or at least it's one way of looking at it. But now I want to show you a totally different way of writing down complex numbers. And your calculator is actually willing to entertain this game as well. There's this other option over here where it says, how about a number out front, and they've got r, like for a radius. And then, this is weird, an exponential where it's e, our classic base, with an angle and then an imaginary number. Right? So this is a totally different way of writing things out. And it does come back to the way you can look at this back here and go, hey, like that blue one. That blue one is 5 big, And if you were to think of a circle that would capture that blue point, the circle would have to have a radius of 5, right, in order to do it. So that's like that R value. And then an angle for it to rotate up from that classic x-axis, from the real axis. And so there was a mathematician who did a lot of work with this, gets his name on this deal, so we should, okay, with all the work that he did. A lot of people think that you would pronounce it Euler, but his name is actually pronounced Euler. And this is hugely important in math. And if you're going on into engineering or science, you need to realize right now that this is very cool, because deployed the right way, it can make very short work of some nasty questions, especially in like electrical engineering. You can turn them into grade 11 physics questions. And here is his expansion. Here's his formula, if you wish. He said, if you ever have e to the imaginary number, this is weird, got a square root of a negative there, multiplied by an angle, theta. It could be any number, but we like to think of it as an angle. That is equal to, so this is like the weirdest thing ever, right? Never had a I up there in the exponent on an e. That's equal to the cosine of that number touching the I, the cosine of the angle, if you wish, plus I times the sine of that angle. This is a truth that you can rely on. And if you take a look, you've actually got kind of like an A plus BI thing going on over on the right. You've got a nice clean real number, and then basically a BI just kind of written backwards, right? Sine theta times the I. But then over on the left, you've got this e to the I times theta, and yeah, we will sometimes put a number, right out here in front of the e. But the Euler expansion generally can leave that out for now, and we can kind of distribute it through later if we need to. But that's Euler's expansion, and let's try this out. So if I had e to the I times 2.5, sometimes written, it maybe sounds a little bit better if you just say, oh yeah, that's e to the 2.5i. Yeah, okay, you can do that if you want. That is mathematically the same thing as the cosine of 2.5. By the way, you must be in radians, plus I times the sine of 2.5 radians. Okay, so absolutely must be in radians here. You can talk in degrees, but when it's time to actually do this, it's got to be in radians. Now, if I do the cos of 2.5 in radians, I end up with, well, let's try this out. Make sure I'm in, yeah, I am in radians. So if I say, hey, calculator, what is the cosine of 2.5 anyways? It says, well, that's negative 0.8-ish. And if I say, hey, calculator, what the sine of 2.5? It says, okay, well, that's 0.598. So we're actually hanging out in quadrant 2 somewhere, where the x's are negative and the y's are positive. So this number that we've got on the screen here is the same thing as negative 0.8011 plus 0.5984 times I. And my calculator will actually do this. One thing to notice just about this, because we've actually got essentially a 1 out here, that's like the R value that we saw in our graphing calculator. What I can promise you is that if you were to go and try out doing absolute value like we saw back here on this page, if you were to say, hey, if I plot this thing, by going 0.8 back and 0.59 up, what's its absolute value? How far from 0 is it? It's actually going to be a 1. Like, I dare you, like take this number here, square it, add it to this number, square it, take a square root. You're going to see that it's actually a 1. But my calculator will do this. This is what's so cool. I can say, hey, calculator, would you mind going and doing, now let me clarify one thing. I'm still in this mode that says A plus BI. So when it gives me an answer back, it's going to give it to me in that A plus BI format. So it should have what I have over there on the right. I'm going to say, what do you think about this? E to the, and it's like, yeah, what do you got? I'm going to put an imaginary number up there, I times 2.5, and it's like, whoa, Euler. And then it comes back and it gives this to me. Now it's long, it's got like 13 decimals twice, but it does have the negative 0.801. It's all there. I just have to wiggle over to the side to see the rest of it, and wiggle way over before I can see the I. I imagine if I had a fancy new TI-84 color edition, it probably lets me see the whole thing. Wouldn't that be nice? Okay, let's try this next one out. These ones here, geez, I can just use my knowledge of special angles. For this one, this would be cosine of pi over 2, otherwise known as 90 degrees, plus I times the sine of pi over 2, otherwise known as 90 degrees. Well, cosine of pi over 2 is nothing, and sine of 90 degrees is a 1, so I'm going to have an I times a 1. Hey, this is just I, actually. This next one, it's not 90 degrees, but 270. So this would be cosine of that 270 degrees. I'll just see if I can get it written in the right way. 3 pi over 2 plus I times the sine of that 3 pi over 2, that 270 degrees. So I'm thinking about the wheel spinning around. Remember we joked about it being a kid on a Ferris wheel. We're going to spin it 270 degrees. The x value is going to be 0, but the y value at 270 degrees is going to be a negative 1. So this answer is actually just negative I. That's kind of neat. Well, with Euler's expansion, you can come up with the coolest equation in the world. This is definitely the coolest equation in the world for many reasons. It is so simple and so complicated at the same time. You look online, you can buy t-shirts with this on it, because math people, hey, we're all nerds, we love doing this math stuff, and we just all know that this has got to be one of the coolest equations ever. And it's just all about taking Euler's expansion for a very specific angle, and then maybe rewriting the equation just a touch. So I've got my little kid on the Ferris wheel, right? There's my unit circle. It's 1 big. Okay, so radius 1. And what if we make the theta that's mentioned here in Euler's expansion, what if we do actually go and make it pi? Okay, so I'm going to spin this little vector around until it's all the way, like over here, like this. So the angle will be pi. So we're going to be out here. Geez, we'll actually be on the middle school number line. We won't be up above it. We won't be down below it. We'll be directly on top of this number line. And if you try this out and say, okay, well, what about e to the I times pi? What would that be? Well, that would be cosine of pi plus I times the sine of pi. Pi is the 180. Cosine of 180 is a negative 1. And then the sine of 180 is 0. So e to the I pi is actually negative 1. Now, you want to make the coolest equation ever? Just move the negative 1 to the left. And you end up with e to the I times pi. Add 1. Believe it or not, that exponential is negative. I know all year long I've been saying exponentials could never be negative. Yeah, with real numbers going in on the exponent. But with that exponent, e to the I pi is a negative 1. And so if I add 1 to it, I get back to 0. So why is this the coolest equation ever? Well, 1, you need to know a little bit about complex numbers to just believe that it's true. And 2, it has all of the important math operations in it. It has adding, like adding and subtracting. It has multiplying, up where the pi and the I multiply together. And it has exponentiation. Okay, that's kind of cool. And it's got equality, right? So it's got kind of all the main math things on the go. Not only that, it has the 5 fundamental math constants all there, and nothing more to clutter it up. You got your 1, really important for real numbers. You got your I, really important for real numbers. You got your pi, really important for circles. You got your E, really important for calculus. And we can't live without 0, right? It's got all 5 important math numbers just all nicely tied together with all 3 math operations: addition, multiplication, and exponentiation. I don't care what you say, that's cool. Literally, you can get t-shirts with this. Look it up. Check it out on your phone. You can buy them with that plastered right on the front. All right, getting closer to the end here. Number 11, regrouping Euler's expansion. I want to just show you a couple of ways that you can shift from one form to the other, because your calculator is happy to do it. If I look at the mode button there, it says, well, do you want to be in A plus BI, or do you want to be in like that Euler kind of game? And it'll freely go back and forth from one to the other. So just so you can see what's going to happen here on this page, for the top half of the page, just so you know where we're going, I'm going to try to take something that's written in the form E to the A plus BI, and I'm going to try to rewrite it into the form A plus BI, not the same A's and B's. I want to leave Euler and I want to get to like just weird adding of reals and imaginary chunks. Euler does not know, well, I'm sure he knew, but the plan with Euler's expansion, it has nothing but an imaginary chunk up here, just like I times theta. There's no place for real numbers to go. But you have a plan based on the work that you did with exponents in like grade 9. You could rewrite this as a multiplication question. You could say this question is actually E squared, okay, that's just a number, multiplied by E to the 5i. The E to the 5i part, that's like an Euler deal. It will have a size of 1. But the E squared is definitely not size 1. It's a little bit bigger. And I can just multiply these through later. So this is E squared multiplied by, now here comes Euler. That'll be cosine of 5 radians plus I times the sine of 5 radians. And if I take my calculator and say, hey, calculator, what's the cosine of 5? It says, oh, well, that's 0.2836, at least to 4 decimal places. And then if I say, calculator, what's the sine of 5? Put that with an I. It says, hey, that is negative 0.9589. And all of that is going to get multiplied by E squared. E squared is roughly 7.3890, right? If I do nothing but take my calculator and say, hey, calculator, math 12 thing here, what is E squared? Yeah, 7.3890. Okay, all I do now is just distribute that 7.3890 onto those numbers. But before I do, worth pointing out that this thing, so far, just with this Euler part, the absolute value for that is equal to 1. That's how the Euler deals work. But I'm going to now scale it by a factor of 7.3890. So I just distribute. That's all I do. 7.3890 times the 0.2836, I get 2.0959. Then the next part, 7.3890 times negative 0.9589, and I get subtract 7.0855 with the I. If I go and find this on this little picture here, or do my best to find it anyways, if I go and find it, it's 2.09 over, okay, so about like that far over, and then down 7.08. Okay, it's a little bit off scale here, somewhere around there. That's where this complex number is. It's clearly bigger than 1 for its absolute value. In fact, its absolute value is that 7.3890. That's how far it is from 0. So, right, we've got a plan for having even complex numbers up in that exponential. And you could go to your calculator, make sure it's in a mode where it will talk to you as a plus bi, and you can say, hey, calculator, just double checking. What is e to the 2 plus 5i? And it'll go, oh, yeah, I can work on that. And it comes back with the same thing I've got. It's a cheap TI-83, so I have to scroll a little bit. 2.0959, yep. And then I scroll over, minus 7.08, and there's the I on the end, so it is actually there. Okay, what about going the other direction? A little tougher, but not impossible. Well, to be honest, the easiest way to take that number, 4 plus 3i, which sits out here somewhere, 4 over, 3 up, by far the easiest way to turn that into something similar to what you see at the top would be to actually just ask your calculator. Put it in that mode where it responds back with like an Euler polar form expansion, we call it, and shove in 4 plus 3i. And we'll try that in the end just to make sure it works. But here's the way that you could do it by hand. First thing you got to do, you got to find or think about the absolute value for this. That's where you say, hey, how far is that from 0? Well, it's middle school Pythagoras. 4 squared plus 3 squared, add them up, take a square root. It's 5. Euler's plan works if you're playing with numbers that are not 5 away, but only 1 away. So we need to do a little factoring. We're going to factor that scaling of 5 out and ask ourselves, hey, what's left? Well, if I divide by 5, I get 4/5 plus 3/5 I. And you now have a little math 12, math 11 unit circle game where you have to say, hey, there's an angle out there somewhere, and the cosine of it is equal to 4/5. Well, that could happen in either quadrant 1 or 4. Oh, but there's more info. The sine of the very same angle is 3/5. Well, that could happen in quadrants 1 or 2. So it looks like we're going to be in quadrant 1 with this deal. And then you just ask your calculator, okay, like where are we? And with a little work, it's really just math 11, but in radians, we can find that this angle is 0.6435. That's the angle right in here. 0.6435 radians. Okay, we're ready to go. Here's how I can write that story in a format that's not a plus bi. I could say, hey, this is 5 times cosine of 0.6435 plus I times the sine of 0.6435. Well, why write it in such an ugly way when you can just do Euler's game, but backwards? And you can say, hey, that's 5 times e to the I times 0.6435. And you're basically there. You're basically there. You could leave it like that, or if you wanted to, okay, that's fine. That's probably what my calculator is going to do if I ask it. If you really, really want to, you could say, well, did you know that 5, if I play around with logarithms, is the same thing as e to the 1.6094? Like, I can just ask my calculator, hey, what's the log of 5? What could I put on an e to get there? And it says, yeah, that number. Oop, hang on, I'm doing something backwards here. Give me 1 second to check this. Oops, had my calculator in the wrong mode. Well, I had my brain in the wrong mode. I shouldn't have said log of 5, right? That's base 10. I should have said ln of 5. My bad. At university, though, your professor is going to say log when they are really doing lns. So yeah, 1.6094 is just fine. And that is then multiplied by e to the I times 0.6435. So you could write this number that was nice and innocent up there. Like, look at this thing, 4 plus 3i. And you could say, oh, I could write that like this. An e with a 1.6094 plus 0.6435i. But like I said, a lot of people might go, oh, you're making it worse than it needs to be. We could have just done this. Could have put a 5 out there. I'm going to see what my calculator does. So I'm going to say, hey, calculator, I'm willing to do complex numbers, but can you chat to me in this format? And it's like, okay, I will chat to you in that format, but you can chat to it in any format you want. So once you say, hey, you have to talk to me that way, you can talk to it this way. You can say, hey, what is 4 plus 3i? And it'll go, oh, well, I can't say it back to you in that format, so I'll give it to you this way. It put it just a 5 out front, and then this exponential with the 0.6435. And if I scroll over, right, there's the I out there on the end. So this is working beautifully. And that takes us to this page here, number 12. How do you divide complex numbers? There's a couple of ways to do it. The way to do it, if you're in the a plus bi format, you have to go and multiply by the conjugate. That should do it. So I'm going to take this story that was nice and innocent, 12 plus 5i, divided by 4 plus 3i, and I'm going to try to turn it into just one complex number, not one on top of another. And so I do that by multiplying by the conjugate, which would be the conjugate of 4 plus 3i would be 4 minus 3i. I reverse the sign just on the imaginary part. But I have to multiply by the same thing upstairs. I got to be fair. I can't go change the value of this thing. Okay, now it's time to FOIL. And yeah, there's a fair bit of foiling to do. Upstairs, 12 times 4 is 48. 12 times a negative 3i is a negative 36i. Got an imaginary chunk. 5i times 4 is a 20i. And then I'm going to have minus 15, but an I squared. So that's actually a plus 15, right, because of the I squared. Downstairs is where the beautiful stuff happens. Just like this worked beautifully with roots, it's going to work nicely here too when I go and FOIL, because my insides, 12i, and my outsides are opposites. So they go away. So downstairs I have the 4 times the 4, which is a 16, and then I have two terms that go away, not even worth putting them in, right? Add them in if you want, 12i, negative 12i. And then there's a minus 9, oh, but with that negative 1 from the I squared. So it's actually plus 9. So tidying this up, upstairs we've got a 48 and a 15. We've got 63 for the real part. And then minus 16i. But downstairs, oh, it's beautiful. It's nice and clean. Nothing complex about it. Just a 25. And if you wanted to write that just as a simple a plus bi, just take the 63 and take the negative 16 and one at a time divide them by 25. 63 divided by 25 is 2.52. The 16 divided by 25 is a negative 0.64. And my calculator knows how to do this too. If I ask it to just double check my work, I am going to change the mode back to please talk to me in a plus bi's. So I'm going to go down here, say I'm willing to do complex stuff, but let's chat that way. And then I can go 12 plus 5i divided by a 4 plus 3i. And it goes, yep, I got it, 2.52 minus 0.64i. Now, there's another way you can do this using grade 9 exponent laws. If you think outside the box and are willing to do a little Euler, you could rewrite that 12 plus 5i. It's not fast, but it can be done. You'd have to go back and do what we did on this page. Like, it's a bit ugly, but you could rewrite it and say, well, how big is that 12 plus 5i? Right, this number here. 12 plus 5i, if you look at the absolute value of that, which, by the way, your calculator can do. If I go, hey, let's do some math, complex math, I can ask it, hey, what is the absolute value, number 5, of 12 plus 5i. At least I think it'll do this. It says, hey, that's 13 big. Yeah, little middle school Pythagoras. If I rewrite this as 13 and then an Euler deal, you can do it. Like it's on the other page. It takes a minute or two. You have to find the angle. It ends up being 0.3947. I'm going to put even a few extra digits here. 91 times I. The 4 plus 3i, its absolute value is 5. And if you do the previous page, it takes a bit of work, but you could write this as an angle with an Euler deal. This is 0.643501i. And then you divide, right? If I take this and divide, well, I'd have to do the 13 divided by the 5. I don't even need the room over here on the side. I'm going to go right here and say that's 13 divided by 5, whatever that is. I'm going to figure that number out in a minute. That's for that part, right? This is all multiplied here and multiplied there. Oh, but now I'm dividing with some powers here, and the bases are the same. And I learned in grade 9 and grade 10, you can just subtract the exponents. So the exponents are pretty darn exotic, right? They're imaginary, whatever. Just follow the rules. So this will be 0.394791i subtract 0.643501i. And you're done. You could write this as 13/5, which by the way is 2.6. That is the absolute value of the number, even if, I know I'm not done yet, but that's the absolute value of this. If you say, hey, calculator, how big is that? It'll say, oh, it's 2.6. And then there's an exponential, just a little Euler part. E to the negative 0.2487i, somewhere in there. So that's just another way of writing the same answer. This answer here is the exact same thing as this answer here. They're both 2.6 big. And they're on that complex plane. And you could have just said to your calculator, if I go back a little bit and say, hey, do you remember when we did this? And it's like, yeah, I already told you the answer. You could say, well, can I change the mode? Can you give it to me like Euler-like? Like that? Polar form, we call it? Can you redo that, please? It's like, sure. It's 2.6, and then it's got this negative exponent. And if I wiggle over, there'll be an I. Yeah, there it is. There's the I. Now, that's the end of this video. There is an extra little video for the next page, actually the next couple of pages, but I'm going to stop this one here. And you'll need to just catch the last little couple of pages with the next video, but that's where this one is done.